Imagine standing in a quiet room and someone turns off the lights. You can't see anything, but you can still feel the room's shape. Where the walls are, where the space opens up, where something heavy moves nearby. That's what modern cosmology feels like.
When we measure the universe, most of what shapes it is invisible.
Galaxies spin too fast. Gravity bends light where no matter is seen. And the universe is expanding. And the expansion is accelerating. Tonight we'll walk through 5 mysteries, calmly and with evidence. We'll separate what we know, what we suspect, and what we're still guessing. The first mystery holds galaxies together like invisible scaffolding. We call it dark matter, not because it's evil, but because it doesn't glow. It doesn't emit light, absorb light, or reflect light. If it were in front of you, your eyes see nothing. But gravity notices. Stars far from the center should orbit more slowly. But real galaxies don't. The outer stars move too fast, fast enough to escape.
Unless something else adds mass. A lot of mass.
The visible galaxy is just the tip of a much larger iceberg. Gravity curves space-time, and space-time bends light. Distant galaxies appear stretched and warped, gravitational lensing. Sometimes gravity is strong where normal matter isn't. In cluster collisions, hot gas lags, but the gravitational mass moves on. It looks like 2 invisible halos pass through the crash. Dark matter seeds the cosmic web, the scaffolding galaxies build on. We can map it with weak lensing, turning the sky into a gravity scan.
But we still haven't caught the particle. It barely interacts.
Possibilities include new particles or a deeper change to gravity.
Modified gravity can mimic some effects, but matching everything is hard.
Direct searches listen for whispers, and so far, hear mostly silence. Whatever it is, its gravity is precise. Its nature remains hidden.
So the first mystery stands: mass without light. The second mystery is not matter, but a push, dark energy. It is the quiet pressure making the universe speed up. In the late 1990s, supernovae suggested as expansion is accelerating. Far galaxies looked farther than a slowing universe predicted. Something acts like pressure in the fabric of space, pushing outward. That something became dark energy. The simplest explanation is a cosmological constant, energy built into space.
As space grows, the effect remains. A steady, everywhere pressure.
If it lasts, the far future becomes lonelier. Fewer galaxies remain reachable. But dark energy might not be constant. It could evolve like a field that would reshape the universe's long-term fate. Surveys now test whether dark energy stays fixed or slowly changes. Some results hint at variation, but the verdict is not final.
Or acceleration could reflect modified gravity on the largest scales.
We measure acceleration in several independent ways. We can measure what it does. We still don't know what it is.
And accepting dark energy leads to an even stranger problem.
Because quantum physics says, empty space is not empty. It's filled with fluctuations, a restless baseline.
And when we add that energy up, the numbers explode.
Theory predicts a vacuum energy wildly larger than what we observe.
This is not a small disagreement. It's one of the largest gaps in physics.
It looks like huge contributions cancel to leave a tiny leftover. That balance feels like fine-tuning, as if reality is set on a knife edge. Maybe a mechanism we haven't discovered forces the vacuum energy near zero. Or maybe quantum gravity changes how vacuum energy gravitates. Some propose many regions with different values, and we exist where galaxies can form. It's controversial, hard to test, and easy to misuse. But the problem remains. Why is dark energy so small? Now we reach a mystery where the universe gives two answers to one question. How fast is the universe expanding today? Our best methods disagree. Early universe data prefers one value. Local measurements often prefer another. The difference is large enough that it might mean more than error.
This is called the Hubble Tension.
Local methods build a distance ladder, step by step, star by star. Then supernovae extend the ladder into deeper space. Early methods use the cosmic microwave background, the universe's ancient afterglow. But that inference depends on a cosmological model. It's like two clocks disagreeing about the same present moment. One possibility is hidden systematics, small biases in calibration. Another is new physics early on, a brief extra component that shifts the scale. Or new physics later, dark energy or gravity behaving differently. So far, no explanation has won. The tension remains, a live debate. And behind all this is an older puzzle.
why anything exists at all.
Because the early universe should have made both in almost equal amounts.
If they were perfectly equal, everything would annihilate. Yet matter remained. Enough to build stars, planets, and us. Somewhere, the rules favored matter by a tiny amount. We do observe differences between matter and antimatter, called CP violation. But it seems too small to explain the cosmic imbalance. To make an imbalance, you need three things: symmetry breaking and non-equilibrium.
One idea. The early universe underwent transitions that created the excess.
Another idea. Neutrinos helped create an imbalance that later became matter. We search for new sources of asymmetry, but the answer is still hidden. Every atom in your body is evidence that symmetry broke in our favor. You exist because reality contains rare, fragile asymmetries. Not because the cosmos was designed for you, but because it allowed you. These were 5 mysteries: invisible mass, invisible pressure, and cracks in our theories. We don't solve mysteries by belief. We solve them by building better questions. And the best part is, you live in an era where answers are moving, slowly, but genuinely. Mystery is not a gap to fear. It is a frontier, and frontiers give meaning to curiosity. If you want more calm journeys into the unknown, tap like and subscribe to Arcane Knowledge. And we'll place the next memory pin together at the edge of the universe.